Great. Well, thank you for the invitation to speak here tonight. I very much appreciate it. I'm here to represent a very large and dedicated group. All right, please heckle as I try to drift my way back. So I'm here to represent a very large and dedicated group of scientists from multiple agencies that are focused on landslide hazards and resultant tsunamis in Prince William Sound. So I represent folks from the U.S. Geological Survey, the National Tsunami Warning Center, the Alaska Division of Geological and Geophysical Surveys, and the Alaska Earthquake Center. So we're all here initially because of the discovery and recognition of the hazard at Barry Arm. So for those of you who aren't aware of the Barry Arm landslide, it's a very large, slowly deforming landslide that was recognized in 2019. Just throwing some, oops, I'm going to be worse at the pointer, I think, than the previous speaker. But I will almost certainly take that title probably in the next 2 or 3 slides. So this is the Barry Arm landslide, northwest corner of Prince William Sound. It's over 1.5 miles wide, 3,000 feet high. And so almost half a billion cubic meters of material just perched on the hillside, slowly moving down slope. So if we look back through the imagery and through aerial data sets that we have going back to about 1999, you can see it's been kind of slowly creeping along, where it started off moving about 1.5 meters per year during our period of record. As the Barry Glacier, which is right here in the center of our image, started to recede in 2010, it really accelerated. So we saw rates up to about 26 meters per year of downslope movement between 2010 and 2013. 2014 to 2016, it slowed down a little bit, but still pretty fast at 10 meters per year. And a good way to stop a landslide from moving fast, hopefully, is to put monitoring equipment out. So since we started really keeping an eye on it, it slowed down quite a bit. So 3 meters per year in 2020, minimal movement in 2021, and about 3 meters again of cumulative displacement last year. So that seems to coincide with the retreat of the Barry Glacier. So the Barry Glacier was off of the image in 2009, and it's kind of been hanging out here since about 2017, relatively stable, the position of the terminus. So upon the discovery and recognition that this thing presents a hazard, we wanted to look and see what would happen if this were to fail. So it's slowly moving now, but we want to know what's the chance that this would actually fail rapidly and catastrophically, enter the water, generate a wave that could have local impacts, obviously, but also region-wide impacts, specifically in the community of Whittier. So initial studies caught the attention of popular media. So New York Times, The Atlantic, all were publicizing the potential 30-foot wave. That was the initial estimate for within the harbor of Whittier. Later on, we did some additional analysis that scaled that back. We're looking at potentially a 7-foot wave in Whittier itself. So while the topic of this talk is pretty serious, I do like to keep them lighthearted, but I do recognize that the hazard out here affects many of you on a daily basis. It affects you, your livelihood, your safety, your family, your friends, the people that do business with you. And so we carry that with us every time we log into our computers, every time we do our analysis. So we recognize that. We recognize that this affects your daily life, and we want to do the best possible science we can so that we can at least get you the information you need to make that determination of when you think it's safe for you with your own personal risk tolerances to go out there. So with that being said, we'll jump into the science part of it. So as scientists, we're interested in asking questions, and we want to learn more about landslides, how they're distributed out in the sound, why they're there, where they are, and what's the chance that they're going to go catastrophically. So by doing that, we ask ourselves a couple of questions. So the first question, where are landslides and corresponding hazards in the sound, and why are they there? Second question is, when do landslides move slowly or fail rapidly, and why do they go from one speed to another? And then finally, how can we use that information to convey to you the information you need to reduce your own risk. So we'll start with the first question, the where and the why. So where are landslides? Well, we go out and look for them, just like you go out and look for fish and mussels and those kind of things. You can also go out and look for landslides. So Prince William Sound is a pretty spectacular scenic place. Lots of pilots out there flying around, lots of people in boats. And we go out there as well. So you can actually see new landslides, especially those that occur over glaciers. This is one that happened in the late fall of 2021. Just an optical observation of a landslide. Somebody reported it to us. We made a note of where it was. We had some idea of when it took place. We can also use satellite methods. So every so often, the satellite passes over. It shoots a radar pulse at the landscape. That pulse returns. And as you pass over repeatedly over and over again, you can start looking at how that return changes over time. And then you can start looking at how the landscape is deforming over that period of record. So a pretty sophisticated technique, and I won't really get in too much into it, but it does actually jump out pretty well when you do see these contiguous areas of blues and hopefully not reds in the landscape that indicate slow deformation. So we can use just regular optical methods of finding things, and we can use satellites to then map and publish these data. Okay, so this photo is, this is up the Berry Glacier, probably 10 kilometers up the Berry Glacier, and this is over in Columbia Bay. Columbia Bay, Columbia Bay, Alaska, in Prince William Sound, yes. So we can do these methods when you can see the surface, but so much of Prince William Sound is covered with water. And we know from what happened in 1964 that submarine landslides were a really big driver in the generation of tsunami and subsequent loss of human life. So we can not see what's happening under the water until we work with our friends at NOAA, and they're able to collect really high resolution bathymetric data that pulls back the surface of the water and lets us see what's underneath. And here you can see, this is College Fjord, Prince William Sound, northwestern Prince William Sound. And these blue polygons that maybe you can see if you're close enough, those represent submarine landslides. The hypothesis being that those were initiated during the 1964 earthquake. So we can go out and map all of those when we do have that really good, really high resolution imagery of the surface of the ocean. So we also want to know what happens after a really strong earthquake. I mentioned 1964. So as the ground accelerates, it moves back and forth, that can mobilize slopes and cause ground failures. So back in 2018, there was a large effort at the USGS to look at where ground failures occurred during a relatively moderate earthquake. It felt like a lot probably for the folks here. I wasn't in Alaska yet personally, but I've heard lots of people say it was intense. And it was intense enough to shake things loose. So we can go out and map landslides after earthquakes. And then we keep an eye, our friends at the Alaska Earthquake Center keep an eye on earthquakes as they're happening. And so if we were to see a big earthquake in the region, we'd go out and try to map landslides and see where they were. So you get the idea of where they are. So you get some sense of maybe the topography or the geology that causes that, but you really don't know maybe why they're there. And so in order to do that, we use geologic methods in the field and in the laboratory to understand the link between the bedrock, the material properties, and the occurrence and size and distribution of landslides. So my colleague Lauren Schaefer is over here. She's pointing what's known as a hand spectrometer at the rock face. And what that does is it analyzes the light return from there and tells you about the mineral composition of the bedrock. And then from there, you can make some inferences about how it weathers, how it moves, how it behaves under stress. My colleague, Sean Lehusen here in the middle image, he's looking at the actual structure of the bedrock itself. So if you look, you can see some angular blocks or cracks and crevices. And so what he's doing is he's looking at the orientation of these things, the aperture or how wide they are, the spacing or regularity of those features, and then makes a map of those over the broad region. And you can put your map of landslides over the top of that and see if there's any kind of special configuration that seems to align with the occurrence of landslides that we identified through mapping. This is just throughout the summer we go out. I think we're out there 22 days last summer doing some of this mapping. So this is just sort of a long-term mapping project to characterize the bedrock. And then finally, we can take some material from these hill slopes, bring them to a lab and squish them and see what happens. And so here you apply stress to the material, you introduce some water to it, and you can see how the material behaves as you twist it, as you squish it. And that gives you some sense of what you would expect the landslide to do should it experience an earthquake, or as it slowly deforms, what's the likelihood it's going to accelerate based upon how those particles behave under stress. So that's what we do to understand the where and the why. But a really critical bit of information is the when, because when you know when they happen, you can start looking at some of the causative factors for that. Was it raining heavily? Did we have an earthquake? Was there a rapid snow melt? Those kind of things that may introduce water or shake the surface and cause landslides. So this is the sort of flagship of what we do out in Barry Arm is our ground-based radar system. So this is a little hut. Oops. So it took me a couple extra slides, and I thought, I still got time. So this is the little hut. It contains a radar system. This is it over here. It's a little yellow box that sits on this 10-foot wide rail. The box slides back and forth once every 6 minutes, shoots out a radar pulse. This is trained back towards the Barry Arm landslide. And so it does that every 6 minutes, and it operates year round. From that, we can see if the landslide is moving. And so this is the type of image that we really like to see in the radar data. So here's a scale. This is millimeters of movement per day. The green, lighter green is 0. When you get down here to 50, the red colors, that's 50, purple's 100, blues are 200 millimeters per day. So when we log in the morning, we really like to see lots of green because that means the landslide isn't moving. One day in August of 2022, we logged in and we noticed that this feature that we refer to as the kite is orange all of a sudden. It had been green the previous day. So we're starting to see acceleration of the landslide in the radar image. And to give you some sense of scale, this distance across here again is about 1.5 miles. So we're looking at maybe 1/4 mile by about 1,000 feet high. So a really big chunk of rock starts moving. This is in Barry Arm, at the Barry Arm landslide. Let's see. A few days later, we've got, I think I might have skipped one here. Nope, that looks like it. Okay, so we're now at the 26th of September here. We see purples, reds, and more purples. And you can see this green here. That's the cliff above the landslide, which doesn't move. So again, we're seeing rapid acceleration of this landslide to the tune of between 50 millimeters per day on upwards of over 100 millimeters per day, and a few spots that are go up towards 150 millimeters per day. So we're able to really well characterize the landslide, the rate at which the landslide is moving, how it moves differently across this very large landslide complex. And then finally, we can get back later to the fall. In the fall, we're at Halloween now, and we're back in the yellow. So the landslide is now decelerating. And that's what we like to see. We like to see either no movement, or deceleration. And so now we're just hovering for most of the landslide, somewhere around 10 millimeters per day. And then finally, as it gets cold, and the hypothesis is as things freeze up, we're now in the early November on the 8th, we're back to green. So during the fall of 2022, this is one of the first times this has ever been captured, is we were able to characterize the start of movement, that increase in velocity of the landslide, and how it actually decelerates and then stops. And from that, we can start learning about the mechanics of the landslide and maybe start figuring out why it's moving. But the important part is to know when it moves. Then we can look at some of the causative factors. Sure. Yep.
Can you wait for the mic? So when did you say that first slide where you saw in the orange, what month was that?
That was August of 2022. It was August 23rd of 2020. 2022. Yeah, last
Okay.
fall.
So are you seeing, I mean, this year we've had like an amazing amount of rain. Has that really shown a lot of significant acceleration in the slide?
Yeah, that we haven't fully processed and vetted those data yet. We did see some acceleration, but it wasn't nearly of the magnitude of what we saw in 2022.
Okay.
Yep.
Thank you.
You're welcome. So we can also do this from space. We don't quite have the same high temporal resolution and the same high spatial resolution, but the same satellites that I showed earlier that could detect deformation over a long period of time can also be used to show deformation over a period of about a couple weeks is the return interval. And so when you see these fringes or this rainbow pattern, that represents deformation. And so this was that area we saw first light up in August of 2022. That was also jives with what we're seeing in the satellite data. And we see the same pattern both from space and from the ground. And so that gives us a higher confidence that what we're seeing in the different methods is in fact real. And then finally, to very precisely measure when landslide failures occur, we use geophysical monitoring. And so in this top image, we have what's known as an infrasound array. It's a network of 6 different elements that actually detect the acoustic wave that's generated from like a rock fall, from the glacial calving into the water. So when the Berry Glacier calves, it emits an acoustic sound wave. You can't necessarily hear it, and that's picked up on these sensors. The movement of rock also can generate seismic waves. And so we have a couple of seismometers that are installed in the fjord as well. So looking at the Barrier Arm landslide, this is from October of 2021, so a couple years ago. If you notice, if you're close enough or online and can see it, in this area, we logged in one day and we see, hey, there's this rockfall that occurred on that area that's pretty much stable. This is what we call the headscarp. But hey, there's this rockfall that occurred. When did that happen? These images are only taken once every several hours, so we didn't quite know the precise timing. But if we go and we look at the geophysical data, so this is the seismic data from that period. This is the trace of that seismic amplitude. And you can see that, hey, there's a bunch of wiggles right here. And that corresponds, the composition of the waves that make these wiggles are of such a set of frequencies that we know that that's probably a rockfall event. So then we can say very precisely time the occurrence of this rockfall by what we're seeing in the seismic data. And we can do the same in the infrasound. So why does that matter? Well, that when you do this, you can start saying we've seen X amount of rockfalls per month. And then if we go to the next month, maybe we see X+2 rockfalls per month. And so that's giving us a sense that maybe there's some precursory motion that we need to be concerned about. And so you can do this for smaller events that are here in the landslide, or you can scale this up and detect landslides across the region and start building a catalog of how big a landslide was, how frequently they occur, and when they occur throughout the year. So once you know when, you can start looking at some of the atmospheric conditions perhaps that contribute to landslide initiation. You can have increases in temperature that introduce water into the soil. You can have heavy prolonged rainfall, like the question from earlier, or you can have strong shaking events. So here, this is that period of movement that I showed in 2022, Our red line here shows when that started, and what we've got plotted is rainfall. So we've got rainfall accumulations measured at different durations. And you'll see here, if you look at this purple line, which corresponds to a 30-day rainfall accumulation, you see there's a pretty good increase in rainfall prior to the start of that movement. Whether or not that's just a simple coincidence or if there's actual causal relationship there, that's still to be determined. We're doing some modeling to try to figure that out. But it allows us to do that when we know when a landslide is moving or when it's occurred. So we take all of this information and we do the sciencey things that we do. But the whole intention of that is to be able to reduce your risk and give yourself awareness of what's happening out in Barry Arm and ultimately in other places in Prince William Sound and coastal Alaska. So the information we're gathering and the analysis we're doing is all to give you an actionable information for you to make your own decisions with. So how do we do this? Well, first we learn from the past, right? So we know many of us are probably familiar with Latuya Bay. Back in 1958, magnitude 7.8 earthquake generated a landslide back here in the northern corner of the bay. That failed pretty quickly and rapidly, generated the wave with the highest run-up recorded. So 1,700 feet of run-up on the other side of the fjord. You can see that it caused fairly significant damage from the run-up and inundation on the shoreline. There were a few vessels here in the harbor, a couple of fatalities, and amazingly, a few people actually rode it out and provided some pretty impressive eyewitness accounts. So we were able to learn from this. This is sort of the type event that everybody is aware of and knows about, and this kind of set the stage for a lot of the analysis that we do today. We can also do some modeling. So I'm taking a risk here with a video, so I don't know if I'll be able to do that from my pointer. Okay. So this is a model of failure of the Barry Arm landslide. We've got water surface height over here and wave velocity over here. So it's kind of a quick animation, but we fail it. We propagate the wave out into the water and we watch the resonance of the wave as it sloshes back and forth in the sound. And from that, we can see what the currents might do and what the wave height might be at different locations. So we can take that and we plot that for this particular location, which is just, this is Port Wells right here, Barry Arm, and back into Harriman Fjord. And we can plot what the time since failure on the x-axis and wave height on the y-axis. And you see that there's the predictions of up to 70-meter wave at this location just a few seconds after the failure of the entire mass of the Barry Arm landslide. We also did that in more distal locations. So this is a couple hundred meters offshore of the Whittier Harbor. So our landslide is up here, Whittier's down here, and our virtual gauge for the model is somewhere over here. And so about 25 minutes after landslide initiation, we're seeing a wave height of just over peak wave height of just over 2 meters in just offshore of the Whittier Harbor. So we have the information we need to understand what the potential range of conditions might be should the Barry Arm landslide fail. And then we use all of the different tools that we have for communicating that to you. So the state has a website that they update once a month at a minimum where you can get the most recent status of the Barry Arm landslide and other things that have been happening out in the area. We use social media to get the word out. We do things like this. We go into Whittier and give talks to school kids and presentations in the community, talks like I'm doing today. At the Tsunami Warning Center, they bring in people from the military, emergency responders, state emergency officials to give them a briefing of what could potentially happen and how we're keeping track of this so that they're aware and can respond quickly should there be a hazard. And then finally, we work very closely with the Tsunami Warning Center to make sure that they are aware of when the landslide starts accelerating. They have tools that they can detect the landslide should it occur and the wave that's been generated, and then they can issue their tsunami warning products. So we have various mechanisms that we use to get that word out to all of you. Again, this is a really big group effort. So it's not just the scientists that have the logos up at the front. It's people that are in this room that have been with us for 3 years, getting us out in some of the worst conditions that you'd want to work in. It's the communities, the hotels, the restaurants. All of these people are so supportive of this effort in helping us do our work. And so I just want to acknowledge them for all of their contributions too. So thank you very much.
Scary. I know Dr. Hickman rather well. I suspect you work with him.
Yes.
So I'm wondering with the thickness of that berry arm,
Yeah.
you know, we're seeing how big it is
Yeah.
when you're looking at it, but how thick is that? And what's the composition of it?
That's a really great question. So it's composed of a material that's formed by submarine failures and the precipitation of material that's generated from a submarine landslide that's then been moved, metamorphosed, and built up into a mountain range it's called flysch. That flysch is highly fractured. It's not a really strong type of rock, and it has this regional pattern of how it dips and the fracture patterns that seem to align fairly well with where we're seeing landslides across the landscape. So consisted of flysch. The second question, part of that question, is how deep is it? It's a really big landslide, so there's not one answer to that. But at the maximum depth, I think we're looking at somewhere around 180 meters deep. But it goes down to 0 near the top and some unknown depth at the bottom.
Right. And you said that you were looking at marine landslides.
Yes, that's correct. Submarine landslides.
And how are you accomplishing that? I mean, if you were trying to mitigate some of that, are you looking at areas that might be susceptible to that? That's a big undertaking.
That's about all you can do is identify where they've happened in the past and try to assess where the hazard would be in the future. Mitigation is really not something that we're able to do, and it's not one of our focuses at the USGS. Yeah.
Do you know, this was crossed my mind earlier today. In the Good Friday earthquake in 1964, was that a localized event that took out the village of Chiniga in Lower Prince William Sound there across on the west side of Knight Island?
That's a really great question. Some of my colleagues at the USGS have investigated that, and their hypothesis and their conclusion from those analyses was that there were submarine landslides that occurred near Chiniga and were a major factor in the generation of those local tsunamis.
Thank you for the information. It's very interesting that you can make all these measurements now, even remotely. But I was curious about the information being transferred into the public zone, public area, politically speaking, in particular. In Alaska, we have all kinds of issues like avalanches, massive movement of earth. In fact, there was just a big one in Whittier, for example. Question is, how do you interact from the data that you've collected with the public community at large in order to effectively change people's mind about the fact that they shouldn't live in geologically active zones? How's that?
Right. And I guess we don't try to necessarily tell people where to live. We like them to just be aware of the hazards that they face in those places that they do live. And we do that through talks like this. We go out into schools, and some of our young scientists like to give presentations to the kids and show them the different techniques that we use and do some exercises. We have informational materials that we'll post. We go on radio shows. You know, we do those things to try to get the word out. So that's the most effective way we can do it. But we really focus on providing information to the community managers, the National Weather Service, the National Tsunami Warning Center, who have the infrastructure, the communications infrastructure to get that message out to a much broader community that we can within the USGS ourselves. So we really have to rely on our partners that have that microphone to get that message out more broadly.
I'll take this one. Thank you for a really awesome talk. I have a question about some of the data that you presented, like the really cool radar pictures and the landslide that started it and then stopped. Would you expect like that kind of heads up warning for a catastrophic failure? Has that been seen in other landslides, or would that just be like a totally different scenario? You wouldn't have that like 30 seconds to respond to a 50-meter wave. You might have the days of buildup, for example.
Yeah, that's a great question. So there's always a chance that landslide could fail without any sort of precursory signal. But if you look back at other catastrophic failures that have occurred in Greenland, in Tanfjord, in part of Alaska, up in Norway, you know, a vast majority of those do show precursory rockfall in the weeks and days leading up to an event, with a sharp increase in that activity as you get closer to the time of failure. So the hope is that, yes, we would see those precursory signals in the geophysics and in the radar that would give us a little bit of extra time, given the short amount of time you have from the actual failure of the event to impact in the local communities, that we really do want to see. And we're training our data set, training our analysis on those data sets to be able to figure out how we can determine if we're seeing precursory signals. And in order to do that, we sort of have to have a long library of events. And having been out there for 2.5 years now, we're slowly getting there. So the question is related to wind speed. This is also a really good question, because so for those of you who might not be familiar, there was recently a fatal landslide in Wrangell. I don't know I haven't been to Wrangell, and I don't know the specifics on the exact rainfall amounts or the exact wind speeds, but we do know it was a pretty windy event. We know that the rainfall it was a lot of rain, but it wasn't an inordinate amount of rain that happened. And so there is some speculation that wind can actually, act on the trees, on the vegetation, and even possibly exert some influence on what's happening with the moisture in the subsurface, and then contribute to landslide failure. I think it's a good hypothesis to start testing. I don't think we have anything in the way of definitive word to say on that yet. So that's sort of the background for that question. Whether or not we are monitoring wind in Barry Arm, we've seen winds well in excess of over 100 miles an hour in the winter of 2021, 2022. But we're not necessarily focused on correlating wind speed with failure of the Barry Arm landslide, given the size and the depth of it and the lack of vegetation.